Okay, now where's all this stuff going? This stuff is going to a YouTube channel. So you go to Chemistry with Dr. Smith. ChemistryWithDrSmith.com. You can just type in ChemistryWithDrSmith.com or www.ChemistryWithDrSmith.com. Now what's up here? There's a lot of stuff. So what you want to do is you just want to click on Playlists. Click on Playlists. And then you find your class. So here I am, Chem 1401, Fall 2012. So you click on it, and then you're, oh, I removed that one, that's right. I didn't have sound on it. So let's, oh, 2 videos. There should be 2 videos. Here, that one, they just haven't got rid of it yet. I don't know why. Okay, they're a little slow. But here's day 3. So it doesn't matter where you're at.
Now there's only one left, right? And one pass, 498.
You remember this nightmare, right? And you can iPhone, iPad, whatever, it all works. Now, what's kind of nice is, if you don't want, I think that voice is just nauseating. Just mute it, but you can fast forward and, right, and look at the different solutions in there, right? Well, I guess it's loading, right? So you have to have patience with YouTube, but it's all there. So sports, wedding, sleeping in, whatever, right? You can watch the class that you missed. Okay, ChemistryWithDrSmith.com. Click on Playlists because then it organizes all the files for you. Okay, so that's what's being recorded right now. Okay. The next, I'm really bad with names if you haven't figured that out already. So the next class, what I want, this already isn't working. So the next class, sit where you want to sit for the first half of this semester, right? And then I'm going to have you sign this thing again and then post it, and that's where you have to sit for the first half of the semester. That way I can get names down. For some reason, all I remember is David Duke. I don't know why, right? Probably because he bugs me the most, right? So come by and ask, right? Victoria, because I forgot your name like 3 times, right? So it takes a while. But so if I have an assigned seating, it's so much easier. But this way, just sit where you want to sit next class period, and then we'll assign you to that spot for the first half of the semester. Okay. Now, where are we? We're talking about stuff, matter, the periodic table, right? Elements, compounds, reactions, all this kind of stuff. And I kind of thought it was neat what Sir Dalton said here, right? It's pretty much impossible to create matter, right? You could just as well annihilate a planet or create a new planet as trying to create an atom of hydrogen. But let's take a look at the molecular level, what you should kind of see in your mind's eye when you hear the word reaction. See if this works.
Silver ions react with chloride ions to form the precipitate silver chloride. In this animation of a precipitation reaction, the silver ions, shown in gray, and the chloride ions, shown in green, are active participants in the reaction and combine to form the insoluble silver chloride crystal. Other ions, called spectator ions, shown here in blue and purple, are not participants in the reaction and remain unchanged in the solution.
So why this is occurring and how it occurs and to be able to predict it is a kind of a big goal what we're shooting for. And all I'm after you to get out of this is that in a reaction, man, this is kind of a complicated one because it's in solution, or it's in water. That's why you see all these little water molecules floating around. But stuff actually has to collide. Stuff actually has to interact for reactions to occur. So, and when we start talking about terms like molecules, this isn't a molecule, right? These guys are molecules. What's the technical word for this? It starts with a C. Well, kind they're all compounds. All this, like these are compounds. You get a bunch of them, they're all compounds. But Cr, some people are named this. I don't think we have anyone. Y, crystals, right? Just this same repeating unit again and again and again. And you can lop off hunks of it, and you still have some of the crystal there. But you can't do that to a molecule, right? You bust up a molecule, it's not water anymore. Okay, so you can bust up crystals, but you can't bust up molecules. Okay, so this guy Dalton, he's the one who, I think that animation pretty much pictured everything of Dalton's theory, but we need some terminologies to make sure we're aware of and use the right words when we're trying to explain things. Desiree, element, compound. What's the difference between those two? Yeah, one type of atom, really good, right? So the smallest unit you can get of any chemical is the atom, right? And how do you get a compound then? Yvette. Yeah, put them together. Now they could be a molecule like the water floating around, or it could be a crystal. Right? Just have to put them in the repeating unit, otherwise it's not going to be a compound. Okay. And then the chemical reaction, I guess, makes the stuff. Okay. Some more terminology here. Notice we've got some A's. All right, see little A's, A's, A's. All right. And then you have B's. Okay, so they're trying to say, okay, all the guys within, what are, I erased. Oh, no, I guess I'm thinking about this question. A elements. They're all referred to as the, starts with an M. A, I forgot this actually, because we never use this. We never really care, but I guess it's the upcoming quiz, so we should know the terminology. Main, the main group elements are all the A's. The main group elements are all the A's. The B's, though, this word we're going to use pretty often, and well, probably much weeks from now, but we'll get into B's. The B elements referred to as the blank metal elements. There's the T. Transition. Transition. Okay. And I think what will maybe help you out is we're going to start talking about all these little elements, all these atoms can take on certain charges. And it's the mains are the ones that they don't have any choice. They have to be a certain charge. But the transitions can pretty much take on anything. That's probably why they divvy up the two. Is the main ones, we're going to see what charges they can take and why. But they don't have any choice. They're always a certain charge. But the transitions, they can really take on any number they want for our purposes. Okay. Let's back up here. Groups. If you're going to point at a group, Stephanie, or what's a group in the periodic table? Now, she has a 50-50 shot at this because it's either this or it's that, right? Yeah, she's right. Group is up and down. Okay. And the reason why they give it the word, and I got to find this demo. I should find this movie. I should have done that this morning. Like, for example, these guys. As you go down, they're just metals. And you plop them in water, they react. But they all react with water. That's why they put them in the same group. And the farther down you go, the more violent it gets. And all right, lithium, sodium, potassium, you might get a little plop, plop, fizz, fizz, or a little flame. But when you drop this one in, the cesium, man, the guy's got the glove, you got the glass shield, his hand's shaking, and you see why when he drops it, the thing explodes and it hits the shield. And so I got to dig that up. It's pretty neat. But they're in the same group because they all have similar chemical properties. They react with the same stuff. Okay. Periods, then, they must be the rows, right? Any period is a is a row in the periodic table. Know the names of the following groups. So since these groups react the same, they're all going to have the same charge too, I guess, when we start talking about ions. But you have group 1A, this one. Group 1A. What do we call group 1A, Victoria? Alkaline. Alkaline. And then group 2A, Ashlyn. Group 2A. 2 words. Anyone know? Alkaline earth. Yeah, alkaline earth metals. Alkaline earth. What's the alkaline word mean? You've seen the alkaline batteries. What's alkaline mean? You get it in water. It's not acidic, but it's basic, right? It's a basic solution. Okay. But that's neither here nor there. Group 7A. Okay, now we're way over here. Group 7A. Brianna, starts with an H. They're not quite from hell, but it's in the word. I guess it's not really hell, it's hal. Anyone help her? Halogens. Yeah. So you've seen halogen bulbs. They use those elements to get that funky ultraviolet blue color. Group 8A. Very last one over here. Maria, these things aren't supposed to, all those elements in that group aren't supposed to react with anything, but under the right conditions, you really can get them to react, but not very well. Maria Gutierrez? The blank gases. Starts with an N. Yeah, it starts with an N. N is in Nancy. Yeah. Noble gases. Yep. Okay. Noble gases. All right. Now you knew it was coming sooner or later. And it's starting. Know the names and symbols of all the elements in the first 4 periods of the periodic table. Ugh. Right? First 4 periods. 1, 2, 3, 4. All those guys. Let's start with, where's Gloria? Gloria Morales. Okay. Oh, this is good timing. Okay, so we're going with Gloria, and then you just keep going down. Okay? So you see the first one, or you can see up here, it's bigger, the H. That is what, Gloria? Hydrogen. Okay, keep going. What do you think? 2. 2 is helium. 3. Where's 3? There's 3. You see it? I got to get my laser pointer here. And where am I seeing these numbers here? I'm just seeing up here, right? 1, 2. Okay, now we're at 3. Lithium. Keep going. 4. Anybody know it? Beryllium. But then you got to spell it. All right. Where's my little beryllium? I've misspelled this thing so many times that I think I finally learned it. It's got a sneaking Y in there. And then the rest goes as it sounds. Beryllium. All right. Next, we're at 5. B. Boron. Good. Okay, keep going. Victoria. 6. Carbon. She got an easy one. 7. N. Nitrogen. Oh, yeah. Oxygen. F. Oh, so close. Iron is going to be this one for whoever ends up with it. F. Oh, fluoride is going to be when you put a little charge on it. But just F with no little charges. You're still close. Not fluoride, but fluorine. Where are we? Ne. Neon. Keep going. 11. It's supposed to be really bad for you, but I don't know. If you exercise a lot, you got to eat a lot of this. Sodium. Isn't that weird? Sodium. How do you get the Na out of the sodium? All this is just historical. Mg. This metal will burn, and it'll get really bright. Mg. Anybody help her? Magnesium. Okay. The cans, aluminum, Blank Valley, Silicon Valley, all right, a lot of computer, semiconductor stuff. P. Oh, so close. Where's potassium? That's going to be this one. What? Not phosphate, but phosphorus. Phosphorus. Oh, man. All right. Let's see. Spell it. Phosphorus. pH. It's all pHs. pH, phos, OS, pH again, because the F's are pHs, and then OR, OUS. All right? Okay. Who have we picked on? S. S. This is what makes your fart stink. Sulfur compounds, yeah, sulfur's in there. Okay, and now we have Cl, chlorine. War gas, they used this to kill people in World War II. Ar. There is this is one of the gases that's in air. Ar. There is some small amount. It's in our air. Anybody know? Argon. K. Someone said it earlier. It was potassium. Ca. Calcium. That's good stuff for us in your bones. Sc. Back at the beginning. This one you probably never even heard of. Scandium. Scandium. Ti. Now, if you get the expensive golf clubs, you get this metal. Titanium. V. Now, this is in the, what do you call those little, that stuff you buy to make yourself better? All those little minerals and things. This is in there every single time. There's the V. Yeah, it's in the vitamin tablet, but vanadium. Vanadium. This is in there too, Cr. Anybody know? Chromium. They add that to, I think, steel. Chromium. Mn. Magnesium was this one. Manganese. Now Fe. Everybody? Iron. All right. Now we're here. Co. Yeah, cobalt. Someone said cobalt. All right. Ni. Nickel. Victoria. They're doing it. As long as you know it, fine. If you know it, fine. Just yell out. So you can beat Victoria to it. Cu. Copper. Right? Cu is copper. Now this stuff they put around things that they put in the ground because this will react before the iron will. Zinc. Galvanized nails. Maybe you heard of that? Galvanized nails. That's zinc. Ga. Gal. Gallium. GE. Not General Electric. GE. Germanium. This will kill you. AS. Sometimes it makes it to the forensic science shows. AS. Arsenic. SE. Janet. SE. I think that one singer, she died. Selenium. BR. Bromine. And KR. Kind of like Superman, but it's not kryptonite, it's krypton. Okay, so the names and symbols of those first four right? I could be throwing any of those on the quiz next class period. Okay. And if you didn't write all that stuff down as we were saying it, fine. Just look in the book. There's a table of all this stuff. Okay. Or Google it. You can get all that stuff. Nuclide symbols. Okay. We are comfortable, I think, with carbon, because carbon was what symbol? C. And so if you have an atom of carbon, that's how you represent it. You have a C. Okay. But it really contains what? Protons. What else is in there in this atom? Neutrons. We're going to get to this later, but protons, neutrons, electrons. So the protons, neutrons in the nucleus, it's surrounded by all these electrons flying around. The whole thing, it's mass, so it has to have some, it's matter, it has to have some mass. Okay, it has to weigh so much. So why even bother having all this complicated stuff? Why not just write C? Now you want to talk about carbon atom, just write C. Why do you have to write mass number and atomic number? What's this stuff? Atomic number is the number of protons. Now, this is why this is a big deal. Not all carbon atoms are alike. If they were, you couldn't do carbon dating, because one form of carbon turns into another form of carbon after about 100,000 years. You get a tree, brand new tree, right? So then it starts out with, everything in nature starts out with this one ratio of carbon 12 to carbon 13. What's this 12 and 13? You'll see, right? But after 100,000 years, that ratio changes. So you can go dig up in the dirt some little old hunk of wood or anything, right? And figure out what that, put it in the machine, see what the ratio is of carbon 12 to carbon 13, see how old it is. But you can do that for a lot of elements, not just carbon. Okay, so they're not all identical. One form goes to the other, and there's these different things. But they call them carbon all the time because they all have the same atomic number. 6. And how do I know it's 6? I don't have it memorized. I just go over here. There it is, those blue numbers. So anything with 6 protons in its nucleus is going to be what element? Carbon. Doesn't matter how many electrons there are. Doesn't matter how many, what's the N one? Neutrons, right? I guess if you have more neutrons, it's going to be heavier, right? Because you have more stuff in the nucleus. But so that's why they have this mass number. That's going to be the number of protons plus the number of neutrons. So when I said carbon 13, that's really what they're saying. If I said carbon 12, okay, it's just the mass number. Okay, so that's why you have to have nuclide symbols, because not all the atoms of an element are identical. So if we're going to play around with this, what is a nuclide symbol? Right? So write this guy for a nucleus for an atom that contains 14 protons and 14 neutrons. Marco, what would you write? Where's Marco? What would you write? 14 protons, 14 neutrons. What's that? I don't know. What is it? Where is it? Oh, not GE, but SI. And where do you put the 14s? Yeah, in those little columns there, right? I wish these were different. I should have made these different, but they're both 14 because they both have the same mass number, atomic number. Okay. To me, it's rare in science when they have redundant information. All these mathematicians and all these scientists, they want to write things with the shortest and briefest way possible. This is redundant. Why is this giving the same information twice? If this is SI, this has to be 14. If this is 14, this has to be SI. It's stupid. This shouldn't even be there, in my opinion. That's how you should write a nuclide symbol. Because otherwise, why? There's no point to write 14 down there. Because it has to be. But anyway, that's what they want you to do. Okay. And, man, you might get out of here early today. Okay. Fractional abundance. The atomic mass. Oh, I'll be right back. I want to get something. Atomic mass. What's atomic mass? Anybody know? Atomic mass. They're on the periodic table. Which numbers are they? It's the bottom one. Yeah, it's the bottom one. So you notice how you get the blue are the number of protons, right? As it gets bigger and bigger and bigger, these things should get more and more heavy, right? And they do. The bottom numbers get bigger and bigger and bigger. Okay, so, but remember, let's pick on carbon, because we've already heard of carbon-12 and carbon-13. So, how do they get those numbers? Well, they need to get the same number, right, a huge number, of those atoms and find their mass. Just in nature, however they exist naturally, find that number of them and mass it. And that's how you get that. Now, they're not all carbon-12, they're not all carbon-13, but in nature, don't go get some petrified tree, just get a tree that's already grown, right, or something. Get some carbon that's fresh, just made. And what's its natural, if you grab, how many of them you're supposed to get? Does anybody know? This is we're jumping ahead a little bit, but 6.022 times 10 to the 23rd. That's how much of this stuff you got to get, otherwise you can't even mass it. So we're talking about something like this amount of the stuff, okay? And you get that much of it, that's going to be its mass, 12.01 grams, okay? And all we're doing here is we're just calculating this stuff, okay? And they're not telling you what it is, but they're trying to say, okay, like carbon-12, this is his mass. Carbon-13, this is his mass. And this is how much there is of carbon 12.609. This is what's kind of weird, I think, too. It'd be easier if they said 70% or 69%, but they already moved the decimal place over for you. Think of it this way. If I said I had, I don't know, 12 things, and half of them were bad, how many are bad then? 6. So you could say 50% is bad, but you didn't multiply 50% times 12 to get it. You multiplied 12 by what? 0.5. You had to move the decimal place over 2 times. You see that? All they did is they moved the decimal place over for you here. So I think it'd be better if they said 69.09%, 30.91%. That's a lot easier to see. Oh yeah, the percents add up to 100. And if I want to find the mass, right, this 69.09% have this mass, 30.91% have this mass. Well, what's going to be the total mass? Just multiply them together and add them up, right? It's kind of like saying if I have 12, half of them are bad. Well, okay. Multiply it, and you get 6. Or similar way, if you had 12, and, well, okay, let's just show you, right? If this is their mass for this 70%, 64.9 is the mass for about 30%, right? Just multiply them. Whatever you get, add them up. There's your total mass. So in these fractional abundance questions, they're really not that bad. And then you can look at this number. It better match with something over here, and you can see what the element is. So this is actually how they calculate these atomic masses on that periodic table. Let's see what we get here. Now it says, don't worry, there's nothing specified about sig figs, so we don't really worry about them. 0.6909. So about 43. I got a mass of about 43.48 grams here, right? From that guy. So 43.48 grams of the stuff is going to be that isotope 63, and 64.928 times 0.3091, 20.07 about. So 20.07 grams of the stuff is going to be 65 isotope. So you add them up, and the real atomic mass is 63.55 about. So which element are they really talking about? Is it copper? I can't see that well. Yeah, there it is. Copper is 63.546. It's the closest one. So they are talking about copper. They didn't, that's not what they wanted. They could have been a part B, what's the element? They just wanted to know what's the atomic mass. Calculate the little number on the bottom, the atomic mass. Okay, 63.55. So it must be copper, but... Okay, one more thing before I let you go. Well, that's supposed to be a U. Where are these numbers coming from? The 63 and the 65. X63, X65. Those are the... Yeah, they're the isotopes of copper. It's kind of like carbon 12, carbon 13. What were the 12 and the 13? Those were the mass. The mass numbers. Oh, they're the mass numbers. So when they say X63, I guess they're really trying to say copper 63, right? The mass number. Copper 65. So copper 65, which one's more massive? 65, right? It's not as abundant in nature, but what makes it more massive? It has more what in the nucleus? Every single time. More neutrons. And how many more neutrons? 2. And I think that's what Victoria or someone's saying about subtracting, right? But that's the idea. Okay. You got the idea. So come by if you have some questions. And we have lab tomorrow if you haven't had lab yet.